calculating a molar heat of reaction from formation enthalpies. So remember, enthalpy is a state function. So essentially, to get your change in enthalpy, you have to sum up the enthalpy of formation of your final states, which is the products, right? So final state minus the sum of all the enthalpy of formations of all the reactants, which is the initial state, right? So just like any state function, like delta T is final temperature minus initial temperature, delta volume is final volume minus initial volume, etc. So we're just going to do the same using our standard enthalpy of formation of products and reactants. But you have to multiply by the number of moles of each species in the balanced chemical equation. And just be careful when you're looking up standard formation enthalpies in the ALEKS data tab that it does matter if it's carbon dioxide solid or carbon dioxide gas, right? It's different depending on the phase of matter. Another thing that will save you some time is if you have an element in its standard state. So look at this O2. We know from like chapter 2 or whatever, oxygen in its standard state is a homonuclear diatomic molecule and it's gas. So the standard enthalpy of formation for any element in standard state, like O2 gas there, is 0. So don't even bother looking it up, okay? So CH3OH in the liquid state, the standard enthalpy of formation is minus 239.2 kilojoules per mole, okay? So you can look these up, okay, in the ALEKS data tab. Oxygen is going to be 0 kilojoules per mole, just putting that out there, right? Carbon dioxide gas is minus 393.5 kilojoules per mole. And then water is minus 285.8 kilojoules per mole. Okay, so you've got to start off with the products first. So, big brackets. 2 moles of carbon dioxide from the balanced chemical equation is minus 390.5 kilojoules per mole. See how the moles and the per mole cancel out? Good-o. Okay. Then we've got 4 moles of water, and the standard enthalpy of formation is minus 285.8 kilojoules per mole. Okay. So that is my products bracket finished. Okay. So I'm just going to end up with a number here. Now we're going to do the same for the reactants. Takes a bit of writing, okay, but we'll get that. Okay, so there's 2 moles of the CH3OH, and the standard enthalpy of formation is minus 239.2 kilojoules per mole. So we've got to be careful with our signs and stuff. Add to that, now I know it's going to be 0, okay, but I'm just putting in here for completion's sake so you can apply this to other things. So 3 moles of oxygen, but it is 0 kilojoules per mole, the standard enthalpy of formation, because it's just an element. So 3 times 0 is 0, but I'm just putting it in there for completion's sake. Now, can I fit this all on one line? Probably not, so I'm just going to leave it like this, okay? So, number 1 then. 2 times minus 393. Can I use my calculator? I don't know. It's highly unlikely. You know, I'm going to pause it because you don't want to spend ages looking at me typing things into my... All right. So for the first one, I got minus 1930.2. And then I can subtract from that. And this is where we're probably going to get like a minus of a minus. 2 times minus 239.2. So that's minus 478.4 kilojoules. So you might want to be careful when I do each bracket separately. So what am I going to end up with? Minus 1390.2 minus a minus is a plus 478.4. It should be minus, whoopsie, 1451.8 kilojoules. How many sig figs am I asked for to the nearest kilojoule? So that's minus 1452. That'll do. Okay, so you just got to be kind of thorough with these. Make sure you're not missing out like stoichiometry, like 2 moles of carbon dioxide and 4 moles of water, like here and here. And be careful with these minus signs for exothermic standard enthalpy of formation, and be careful if you end up with like a minus of a minus, that gives you a plus, that kind of thing. Okay, so nothing too difficult, but just be careful. All right, have fun with that.